I audible? Yes? All right. Cool. So I think first of all, I would like to thank the PingCap team for having us here, inviting us here, and talking about our story experience with TiDB. My name is Vaidyanathan, and I'm a senior engineering manager at Flipkart. I'm part of the Central Platforms group, and we basically manage all of the SQL workloads in Flipkart. And my colleague Reeshabh, he will be with us soon as part of the demo. Reeshabh will be looking at it, and so maybe we should get started. So the Flipkart scale, I hope everybody in this audience at least has heard of Flipkart. We've got about, Flipkart today covers 97% of all of India's pin codes. We have 500 million users and 83 state-of-the-art warehouses across the country. We've got 3 data centers, hybrid, we have on-prem, and we're also tied up with GCP. And a lot of these numbers that you see here are largely, everything is in millions at this point in time. And established 2007, right? And we have been, we are working with TiDB for a couple of years now, I would say. So I think the talk is largely about how our entire experience with working with TiDB. So we'll start off the talk with the whole tech landscape about Flipkart. So we'll talk about 3 parts of this whole journey of Flipkart. There's the pre-order path and the actual ordering path and the post-order path of the world. When you look at the pre-order path, when somebody comes to the Flipkart application or the website, right, they actually look at the whole, whatever you want to buy. So this is typically called as the discovery funnel. Post that, there's something called as the order path. And in order path, you've got all of the checkout, payments, and all of that stuff where people actually put it in their cart and sort of check it out and check out the product, start paying for it, which goes into the accounting part of the world. And subsequently go into the more complex part of the whole supply chain and logistics, which has fulfillment, which talks about which warehouse the order has to go to, and a lot of the warehouse management systems and seller systems. And then finally, once the product is out from there, it also goes to the city logistics and the actual logistics, which goes from mother hub to a delivery hub and all of that, which is basically your first mile, last mile. And then eventually, you basically get your product delivered at your home. Now, when you look at this, and when we're talking about, you could say pre-2021, when you look at the SQL store side of things, this was a state of things. We had MySQL in most parts of this entire journey, if you look at it. We also had a couple of Vitess clusters, and the MySQLs that I'm talking about could either be your single standalone MySQL cluster with a lot of replicas, or it is also potentially sharded clusters where you're sharding by one or the other keys. So largely this was the distribution. And of course there are challenges with MySQL. I'm sure a lot of you also would be aware of it, but I'll still talk about it. MySQL typically comes with an availability hit whenever there's a master HSB failover. Your nodes do fail once in a while, especially we are on on-prem. So with on-prem, the probabilities of some of these things happening are more frequent than a much larger fleet. So every time the master goes down, there is a small duration for which the availability is typically hit. Secondly, in MySQL replication, most people typically follow the asynchronous replication side of things, which means there is no zero data loss guarantee, which means if the data is not replicated to the other hot standby, potentially you could also lose a little bit of your data. The third problem is vertical scalability limitations. In our data center, we have the virtual machines that we create, largely they end at 3.5 TB. So which means you can't really scale beyond that. You are forced to sort of shard your data and sort of expand there, which basically brings a lot of operational challenges there. This is largely what I talked about, the horizontal scalability problem. And then finally that it's not really a cloud native solution. MySQL is not really cloud native. So if your organization is largely going towards Kubernetes and all of that world, then this is a little bit of a challenge in that perspective. So where did TiDB really provide I mean, where was it sort of making the difference? I think one of these things is, the main thing I would say that TiDB provided was, of course, solving all of these things, but in addition to that, it was also MySQL compatible. Where this helps, where this helped Flipkart rather, is that, the amount of work that our application teams had to do to, adopt TiDB was far lesser than adopting a completely different tech stack. So, back to the same picture that we just spoke about. The current SQL stores, if you look at it, largely the entire path has now, I mean, whether you look at your order path or your post-order path and rest of the systems, you see that a lot of them have been replaced with TiDB. We, of course, also continue to have MySQLs because I think in Flipkart we want to make a, there's actually like a, we expect people to actually go through, what kind of use case works well with MySQL, what kind of use case works with TiDB, and then accordingly we expect people to sort of choose this or that. Eventually, it's a cost decision that people have to make, cost versus the kind of what you're getting for the cost, right? What you're paying for it. So that's what it is. Which brings me to my next slide, where things very straightforward. Moving to TiDB, I think it should come as no surprise. The answer is no. It was not straightforward. So what were some of the challenges that we faced when we were moving? The first part, I think, is the narrative, right? I'll talk about each of these things subsequently, but then narrative as in TiDB, when we started about a couple of years back, TiDB, like I think we already came to know that it was not very popular in India, right? It was still an emerging technology, so people were a little wary about this whole new technology, and there were a lot of misconceptions around the whole technology of what it would provide. Some people really thought it was magical, some people thought it was not magical, and all of that stuff, right? So we had to sort of debunk a lot of those things. Second is deployment at scale. So Flipkart has a massive number of TiDB clusters, and deploying all of that at scale presented its own challenges. Third big challenge that we faced, because just to set the context, we don't have one single TiDB cluster serving all Flipkart's use cases. So every tenant basically gets its own standalone cluster of sort, tenanted kind of thing. So alerting was a really huge problem. We were bombarded with alerts, and it's called the alert hell, as some of you might know. The next challenge that we had faced was debugging. Debugging was not straightforward. TiDB is a new stack. You don't get enough, I mean, it's not as, when you look at community side of things, MySQL is at a very different level, of course, also because it's, over time, it's a much more well understood product. So debugging some of these things was quite a challenge for us. And we'll talk about how we solved some of these things as well. Recovery side of things, I'll talk about this too. And maybe you can go to the first one. So first challenge, changing the narrative. A lot of the people, when we started talking to them saying, hey, we need to move your this thing to MySQL, there was a lot of comparison with MySQL. The first question was, hey, it's the same hardware, so why is the performance low? Why is the latency low? Why is the throughput not as good as I would expect from MySQL? So people were comparing the same hardware, but then they were not looking at what the additional benefits that TiDB is sort of giving, right? So we had to change the perspective, saying, hey, you're paying something different, right? So you're paying with hardware for some of the additional features that are coming with TiDB. So you shouldn't be comparing. That's a wrong comparison of sort. So then we had latency and throughput challenges initially when we worked with TiDB. Initially we were running on virtual machines, but then we moved to Kubernetes. So there was a good amount of difference between Kubernetes, which was running on virtual machines, versus Kubernetes running on bare metal. So higher, better performance we started getting, and almost equivalent to MySQL. As part of this, again, changing the narrative side of things, we actually did one experiment within Flipkart where we tried to see what is the max we can typically go with our hardware, on-prem hardware, and we were able to reach 1 million QPS at 7.4 P99 and 120K writes at 13 ms. And once we established that, okay, these are the limitations that, I mean these are the new benchmarks rather, right? A lot of the teams within Flipkart were also convinced that, hey, this actually works for them. And they started viewing TiDB very differently. Before that, it was, hey, it's a very latent system and stuff like that. So this experiment or benchmarking experiment actually laid the way for a lot of people adopting TiDB. Then came the next part, people were also comparing, how much disk it's using, right? Is it using too much disk or all of that? So when we look at MySQL standalone cluster versus TiDB, there's generally also compression that TiDB gives. So, it's roughly, so we scale it about 2.3 times whatever MySQL was scaled at. And finally, there's also this misconception that a lot of people had that it's almost like zero changes. Your application is running on MySQL and absolutely zero changes. You just change the DNS endpoint, right, and point it to a TiDB cluster, and it just runs out of the box. I feel that's not exactly true. There are some minimal changes that are required for every application. There are some queries which work well here, some queries which work well there. You might need to tinker around a little bit, but then once you get to that stage, it's definitely minimal, but then it's not zero. So the second challenge, I mean, this is in the order of 0, 1, 2, 3, like how typically we have. So while this is a second challenge, I'm just calling it challenge 1. Deployment and scale. So the deployment options we had started off with virtual machines in 2021 when we started off, but then we quickly realized that there are too many components in TiDB, and then recovery with that whole failure recovery and all of that was getting pretty challenging. So we decided to move to Kubernetes. And the biggest challenge, or not the challenge, I would say the biggest advantage that Kubernetes gives you, this whole deployment on Kubernetes, is something called as the operator. Is everyone familiar with the word operator? Okay, maybe may not be, but operator is almost like a robotic agent, right? Which is living on your Kubernetes cluster, and it's looking at every change that's happening there, and then automatically making changes as well. So there's a TiDB operator, Kubernetes operator that you can deploy on your Kubernetes, which takes care of a lot of this failure recovery automatically. And one Kubernetes cluster, we had one operator largely for that, and multiple deployments could be, we could do multiple deployments of TiDB on that same Kubernetes cluster. So this allowed us to scale significantly. And then we also built a full-blown platform for complete self-serve, so that when people come to different teams come to us, they'll be able to basically create their own completely self-serve way of creating TiDB clusters. So that's what we did. Second thing is alerting at scale. Now, when you think about all of these clusters going on Kubernetes, there's a small pyramid that, just to sort of underscore the point, we were hit with a massive, like I was saying, alert hell, right? Like alerts coming to us massively. So there are 4 layers over here typically, right? First is the Kubernetes control loop, if you're aware of what I'm talking about. This is the first level of auto recovery, right? Kubernetes itself has some level of auto recovery. When a component fails, it recreates that component and then tries to do something. The second layer is the operator layer, which I spoke about, the TiDB operator, which also does some amount of failure recovery. Every time some component goes down, it sort of does a little bit more intelligent kind of a recovery. The third part is something called as the management plane or the control plane, which it looks at something beyond that. So if this is not done, that is also not able to take care of the below 2 layers, and the third layer is taking care of it. And only finally, when none of these layers are able to recover automatically, the human comes into the loop. So you have to be really careful here. We were getting alerts all the way from the bottom stack, from the operator we were getting, from the control loop we were getting, and from the management plane. So we were getting alerts all over the place. So this is something you need to be careful of when you're deploying this. So what we at least did, we looked at all of our alerts, and then we removed the ones which are already being managed by the operator or by Kubernetes and all of that. And we also bifurcated all of these alerts into 2 parts. One is a platform-related alert and the client-related alert, so that the actionable part is also very clear who's responsible for what. This actually significantly helped us subsequently in managing all of these clusters. The third problem which I spoke about is debugging at scale. So what were some of the strategies that we did to support this, to build the support at scale, right? Like once you have rolled it out, a lot of people are using TiDB, but then, they also need help in figuring out, how to work with this thing. I mean, one thing is, if you've used TiDB, you would see that, they've got a massive number of, when you look at dashboards or metrics, there's quite a lot of them in TiDB. You could even get lost into that whole maze of alerts there, metrics there. So you need to know what to look at, you need to know what you need to evaluate, so that's one challenge which typically comes. We worked with the PingCap team, and then we enabled TiDB training and workshops for all our internal users so that they are a little bit more comfortable with, working with this. I mean, it's not a straightforward system, right? It gives you a lot of advantages, but of course it's not going to be straightforward. So that training actually helped quite a lot. People were becoming more comfortable with going to these dashboards and then debugging some of these things themselves. Then we started building our own chatbots. We are in the AI world today. It's a first-class citizen today. So we started building our own chatbots and to solve a lot of these common issues. When people come and ask, hey, this is not working as it's expected, too lazy to sort of see what's actually causing it. But then that's the new world today. We expect answers to be given upfront. So detailed documentation is there, but then this also sort of started helping some of these things. And finally, we of course use PingCap support for more complex and unknown issues which we are not able to debug and figure out on our own, and they have been pretty helpful for all of our sale days typically, and I'm hoping people have heard of Big Billion Day here. So PingCap team is generally available standby in case something goes wrong, and it's been really successful, I would say, all of the Big Billion Days. And last couple of Big Billion Days, in fact, TiDB was some of the technology which was powering all of the supply chain and logistics. And finally, we have also been advocating the use of TiDB.ai. This is not covered so far, I'm hoping, but if you guys take a look at it, please take a look at it. TiDB.ai is a new offering from the PingCap team that lets you debug some of the things, or any questions that you would have about TiDB. It's actually pretty helpful. To a reasonable extent, it's able to solve some of these questions. So we started advocating the use of that. That also helped. Fourth one is recovery at scale. The on-prem thing, right, I was talking about on-prem. So Flipkart has 2 data centers in the country, and we also are tied up with GCP as part of a hybrid cloud strategy. So while, of course, the on-prem has a massive advantage in terms of cost, and that's the reason why we are using on-prem. And because this is a smaller footprint, right? Like compared to a public cloud, it's a smaller footprint. So the probabilities of hardware and all going is definitely higher, which means disks can fail sometimes, and a lot of failures can happen, and this is expected in a smaller this thing. So while recovery is inbuilt, you have got the, like I spoke about, the operator which is there. It is looking at a lot of these things. Kubernetes is there, and they are also recovering their fair share of things. But then whenever these recoveries happen, you've got to also rebalance stuff around the cluster, and whenever that happens, there is definitely an impact on performance side of things. And here I would also like to talk about a little bit more technical stuff here. In Kubernetes, there is something, you can choose different kinds of disks in Kubernetes. There are 2 options that you typically get. The network attached storage, or something called as the local attached storage. Network attached storage basically says that, hey, your disk is separate and your compute is separate and your disk is separate, while your local attached storage says that, hey, the disk and the compute are co-located in the same pod, or node rather, right? Now, we started off with local attached storage because that was pretty mature in Flipkart. And then we realized that the local attached storage comes with its own set of challenges. While it gives great performance, but then from a recovery perspective, every time the node goes down, the storage also goes down, which means you have to actually necessarily have to start rebalancing a lot of this data around the cluster. Slowly, we started moving towards network attached storage, and network attached storage, the biggest advantage is every time the node goes down, the storage is still there. So you can bring one more node up, and then you can connect it back to the same storage, and then that basically ensures that you don't have this rebalancing kind of a thing. So that is something that significantly, I would say, helped us. So if you are starting off on this journey, I would definitely recommend you to always use the network attached storage instead of the local attached storage. Even though the performance, there's a performance hit very clearly, but then from a recovery perspective, that is something that is definitely advantageous. What we also built is, we also built our own operator that works alongside the TiDB operator, right? So, right side is the TiDB operator and the left side is the Flipkart's own operator. And what this basically does is, every time there are problems with the, I wouldn't say problems, right? Every time there's any kind of failure in, or expected failure or scheduled maintenances that are being planned in the data center. For example, in a data center, people would come and say, hey, this particular rack, I'm going to take it down, or this particular node is going to go for refurbishing, this particular disk is going to go, or I'm going to upgrade this thing. All of these things are planned activities. And every time there are planned activities, we don't want it to go in an unplanned way, in the sense that data center operations will happen, of course, in the daytime for the data center people. So every time that happens, we don't want the impact to have to be seen on all of these various services and all of that. So we have an API with them. So every time they are going to do some kind of destructive maintenance of any kind of node, we come to know about it through something called as CRDs, which Reeshabh, my colleague, will explain. And once we know that this particular node is going to go down, these are the TiKVs, or these are the TiDBs that are going to get affected, we proactively start moving out all of these things in customer lean time. Whenever the service has a lean time, maybe in the night, 2 o'clock to 3 o'clock or something like that, we start moving out some of these things to ensure that there is absolutely no impact. So when the actual maintenance happens during the day, on the time of, on the date and time that it was supposed to happen, at that time there is, we have already moved out of all of these problematic nodes, so there's absolutely no impact. So I'll hand it over to my colleague Reeshabh for the demo part. Thank you, Reeshabh.
Thank you. Thank you, Vaidi. So yeah, I'll continue with the demo part of it. So like Vaidi had already mentioned, we deal with a lot of scheduled maintenances because our on-premises cloud that we are using is pretty mature. So we have a lot of these maintenances over a few nodes going down every month or so. So in that case, we have to have a method to basically automate the entire flow, because we don't want ourselves to deal with all of these migrations, these movements. So yeah, so basically we have a contract with the KTS Infra team, and basically they create a volume maintenance CRD, which is internally read by our Flipkart operator, what Vaidi had also mentioned. And what it does, it creates a RIL scheduled maintenance. It creates a TiDB maintenance CRD on which the operator basically picks up and works as per the flow, which I'll get into now. Yeah, so first of all, the KTS admin, which is basically what we have currently, this flow is also automated, the applying of the CRDs and all of those things. So our operator is continuously watching on that CRD, and whenever it notices any change, it basically reconciles as per the controller loop. So for example, when it adjusts the state that we got a new scheduled maintenance, for example, and it makes the changes directly to the TiDB cluster. Now that TiDB cluster actually, basically first of all, it scales up the TiDB cluster so that there is no performance impact during the scale down. Basically, so that there is no issue, there is no performance impact when we eventually remove the node that is going to go for scheduled maintenances. So yeah, for example, we added a couple of nodes here, and rebalancing happened. Now, once that rebalancing is done, the expectation is that we'll remove the node. All of this I'll cover in the demo, actual demo as well. This is just an overview. Once that rebalancing and the removal of the node that is supposed to go down is done, then we basically recreate that node with a new PVC on a new node. So one more thing that our KTES admin infra team does is that whenever these maintenances are scheduled, they cordon off the nodes that are supposed to go for maintenance, which means any new PVC or pod that is created will not be created on those nodes. So that way, once this is done and the rebalancing again kicks in, and basically all of those nodes are get the data basically. Now basically we are over provisioned at this point because we did add a few extra nodes so that there is no performance impact. So the final step is that we remove the extra TiKVs that is added, TiKVs, or it might be any other component that is there. So this is then executed, and we eventually then we go back to the same state with the maintenance as complete. So yeah. So this is an example. Okay, the quality is not very clear. Okay, can we improve that? No, I don't think so. Okay, so basically, as you can see here, so I'm currently running, I have deployed a new KTES cluster, and I'm currently running a basic YCSB load for some workload to be running while this entire process is happening. So this is our cluster that is created. It's 751 version in the like 2 GA back, basically the version currently it is. Yeah. Now, as you can see, so we have, for the purpose of this demo, we'll cover a manual scheduled maintenance that I'll be creating. So this is a scheduled maintenance where we basically have the details on what is the PVC, what is the pod which is going to go down. So this is basically, for example, in this case, it's TiKV 0 which is going to go down. Now we are seeing like the load has already started for the purposes of this demo. Now we'll basically just apply this Rigel schedule maintenance object to KTES, and we'll see the TiDB, we'll see the operator that we have built, the Flipkart operator will kick in and basically start the maintenance flow. So yeah, so currently you can see this is the cluster also you can see. So yeah, now I have applied the object, RFM object, which you can see here. Yeah. So once this is applied, we'll start to see the maintenance begin. The first step of the maintenance, like I had mentioned, will be the scale out of this cluster. So that scale out has happened already. We have seen an increase, like you can see a new pod has started. So TiKV 5 has started, where earlier there were total only 5, now it has scaled up to 6. So what this will happen is the existing, the rebalancing will kick in and the existing load of the cluster will be shifted to 1 extra TiKV. So yeah, the dashboard is taking a little bit of time for that to get affected. It doesn't pull continuously. So yeah, you can see in this, it has increased to 6 now. So that is the first step that is there. Now our reconciler is basically has a time loop of 5 minutes. So every 5 minutes, basically it is pulling the current state, and based on that, it is performing the next step. So since the current state is that we are at 6 TiKV, so the scale out is completed, the rebalancing will be in progress, and there is no impact because of that on the cluster itself. So basically the operator will see this and it will move on to the next step, which is basically to remove the TiKV which was supposed to go down. In this case, that was TiKV 0. So basically, in TiDB, if any store has to be deleted, we have to delete that store first and then delete the pod in PVC. So whatever, as per that flow, what it is, basically we go and we delete the store. You can see that once the store is deleted, it is showing up in the offline stores part. So yeah. So now we can see that this flow is not, there is no impact on the cluster. We cannot see any issue or anything like that. Once the deletion of that store has happened, all the regions of the data that were there in that cluster, in that TiKV, have to move out of it before the pod and PVC deletion can be done. So one more thing, this step, what the moving out that is happening, this is basically a safe moving out because this TiKV has not stopped serving data. So basically the leaders have moved out and the regions are currently moving out. Even if another TiKV because of some issue or something like that goes down in the meanwhile, this cluster will not see a downtime. Basically there will be no significant impact even in that case. This is the advantage of actually scheduled maintenance versus unscheduled maintenance. Because in case of unscheduled maintenance, basically that TiKV has already gone. That is not the case here. We have just deleted the store. The pod and PVC are still available. So yeah. So what you can see that the store is deleted and the regions have started to move out. Currently the data that I had filled was not that high, I think 25-30 GB per replica. So so it's basically started moving out and it will take like around 2 to 3 minutes for. So basically around 4-5 GB of data, it takes like a few 2 minutes kind of a load. In our production clusters where we have a lot of data, basically this process can take up to like a few hours, 1 hour to 3-4 hours also, even more in case of a huge cluster. This is also basically depends on how much your other nodes have capacity and what is your current usage. So all of those play into the part of rebalancing speed basically. So yeah, and we usually try to keep this rebalancing speed as somewhat low so that the cluster impact is minimal. So yeah, here we can see the, basically it will wait for 5 minutes for the reconciler to kick in again and start. So while that is happening, so in our case of scheduled maintenances, because of the volume of what we see, the number of scheduled maintenances that keeps happening. For example, like I was checking yesterday and in the past month, there were like 20 scheduled maintenances of the sort that were there just in March. So, and because of the scale of the number of TiKVs and TiDBs and all of the components that we have, we see a lot of these things. So basically, individually, if for example one of them came and we want to do it automatically during some kind of a lean period that we have. For example, there is a scheduled maintenance which was supposed to happen at the night. Sometime during the night, it needed to be executed during the night because that was the lean period. So in that case, we are not expected to stay up at that time and actually execute this manually. And the sheer number of these things happen, it makes manually doing it very difficult. And I think up until a year ago, that was what we were doing. Because we didn't have this operator, and even though the steps were not complicated, but it had to be done at a particular time and all of those things. And for example, in this case, the rebalancing is taking 2 minutes because the cluster is small. In case if it is taking a few hours, you will have to wait for it to perform the next step. Basically, so that automation there has reduced our headache a lot. So yeah. Okay, so yeah, I think the reconciler will kick in for the next step. So the next step basically will be that it will recognize that the entire regions from the TiKV that was going down, in this case TiKV 0, has moved out. The moment it has moved out, it will see that now it is safe to delete the pod and PVC and recreate it. So the volume basically can be recreated on a new node. So that will be the next step. And once that is done, the rebalancing will again kick in. Basically, all of the regions that had moved out to all the other TiKV stores will start to slowly move back in. So yeah, you can see here that the rebalancing is complete. So rebalancing status is checked and count is 0, and it has deleted the pod and PVC. So again, it reconciled and it performed the next step. You can see here also that the pod went into terminating and now it has started being recreated. Now this pod, yeah, it has come into running now. And so basically now, like I mentioned, the it will start to come back. All of the regions that had moved out and all of the extra regions will start to come back in again. Now the next step, basically once that is done, this step is done, the final step will be basically all of these, the scale up that we had done from 5 to 6. Now we have to reduce that back to 5, basically. So that also requires one more action that needs to be done. Once this rebalancing is complete, then that will kick in. So again, because of the reconciler time, this will again take 5 minutes. I'll not wait for that long, I guess. So we can see that all of the latencies and everything, the time, the throughput and everything, throughout this entire process, we have not seen any significant change in anything. So this is the flow, and basically, yeah, the final step is pretty simple, similar to the scale up that happened. It will scale it back, and as part of scaling it back, it will basically remove all the regions from TiKV 5, the 6th TiKV that was created, and it will then delete the pod and PVC after that is done. This is basically, so in this entire flow, basically our TiDB operator as well as Rigel operator, that the Flipkart operator that we have created, basically they work together. Basically all the triggers are being done by the Flipkart operator, and all of the actual moving out of the regions is handled by either the TiDB operator or TiDB itself. So yeah. As you can see, the status at any time in this entire flow, the status is basically directly being updated in the RFM object, the Rigel Schedule Maintenance object, which is there. And basically, so yeah, that is the entire flow that is there. Yeah, that's all we had. So thank you. In case there are any questions.